Hi, everyone. I'm Nora Bradford. I am a second-year PhD student in cognitive science at UC Irvine, and today I'll be talking to you about a project looking at metacognitive sensitivity and online learning. So a lot of you are probably familiar with metacognition in the context of psychophysics and perceptual experiments, where we might be looking at how a person's confidence tracks their perception of dots on the screen or something really controlled like that. In this project, I'll be applying some of those tools that we use in psychophysics, especially for analysis of metacognition, to a real-world data set from an interactive textbook tool. This interactive tool is called Inquisitive, and it's used by a bunch of undergraduates across the country. It's made by Norton Publishing, and it's in 2 of their online textbooks. In this project, we're just looking at students from UC Irvine for the last year, so from 2 quarters, but we can get access to more of the data eventually. So we're hoping to expand this project at some point. But for now, it's just 700 students. For each quarter, they do 5 inquisitives. So they do 1 inquisitive at the end of each chapter. And for each of the questions in each of the inquisitives, they can answer their confidence on a 5-point scale from I have no idea to I know it. And importantly, they're not just rating their confidence, they're also wagering points. So at the lowest, they can wager 20 points, and at the highest, they can wager 100. So there are some issues and complications with this data and with this task. The biggest one is that students don't have to engage with the slider at each question. So they can just leave the slider where it was for the last trial. So that sort of complicates the data, but we've found some ways to work around it. Just before we dig into some of these analyses, I wanted to situate us in SDT, specifically type 2 SDT. So we have hits, misses, false alarms, and correct rejections. Here, a type 2 hit is defined as getting the question correct and having high confidence. And high and low confidence are defined per person based on a median split for their own confidence ratings. And then a type 2 correct rejection would be getting a question incorrect and having low confidence. And then you can fill in the rest from there. We'll also be using a receiver operating characteristic curve, and this is used to evaluate classifiers. So it's often used in medical contexts, but here we're going to be putting type 2 false alarm hit rate, or type 2 false alarm rate, sorry, on the x-axis and type 2 hit rate on the y-axis. And the area under the curve here indicates how good a student is at classifying their type 1 performance with their confidence ratings. So the larger the area under the curve AUC, the better of a classifier they are. So here are just 2 examples sort of showing each end of the spectrum. Here is a student that is very good at classifying their own performance with their confidence. They have a high area under the curve. And then here's a student who has a very small area under the curve. It's pretty much at chance. So that's sort of what we're working with. And because this data is kind of messy and it's a big data set, we wanted to just do a sanity check really quick. So the first thing we looked at was what I'm calling percent change. And this is basically the percent of trials where a subject changed their wager from the previous trial. So they didn't just leave the slider where it was at for the previous one, they actively went in and changed it to a different point on the scale. And with this, we see what we would expect, which is basically that percent change tracks AUC very well. They have a tight relationship. And that means that students who interact with the slider are tracking their performance with their confidence, as expected. And then the second thing we looked at was the interaction between area under the curve and correctness, so percent correct for the entire class per person. And we see this slight upward trend, which we would expect that there to be a relationship there, but it wasn't significant. And that was sort of surprising. So we wanted to clarify why that might be. And our first thought was maybe that this is just sort of clouded by the fact that a lot of students aren't interacting with the wager because they don't have to. So we tried using a cutoff, and this cutoff is pretty conservative. It is basically looking at people who interacted with the slider more than 15% of the time. So that's a pretty low bar. And with that, we see that there is this significant positive correlation between percent correct and area under the curve. So that makes sense. This particular one is a weighted correlation, looking at percent change as the weight. But importantly, this is also significant when we look at a non-weighted correlation, and it's significant when we make the cutoff 10% instead of 15%, so even more conservative. So this is a pretty robust finding. Next, we wanted to see if there's any relationship between area under the curve and performance over time. Intuitively, we thought that maybe students who have higher AUCs are better at studying, and then they get, improve in the class over time. And so we wanted to see if that was true. And we first started with looking at the fall quarter data, and we saw that students who are in this low AUC bin and high AUC bin perform pretty similarly, and actually the low AUC bin is doing better at the beginning. But then they cross, and the high AUC bin ends up doing better for a couple of these chapters, and then finally they end up doing pretty much the same. But then interestingly, in the spring quarter, the high AUC bin is consistently performing better than the low AUC bin. And we see that towards the end of the quarter, they're diverging even more. So this is sort of an interesting result. We don't know if this is causal or not. Basically that if the AUC is causing people to improve, or if it's just that students with high AUCs tend to just do better in the class, but not because of their metacognitive sensitivity. So that's to be explored. Hopefully we'll have stats on that soon. And finally, I just wanted to talk about next steps really quickly. So one thing we can look at is Norton has rated the question difficulty for each of these questions separately from the data that we're looking at. And we wanted to see if there are maybe some effects of metacognitive sensitivity with difficulty, because that would be sort of an interesting interaction. Are students better at metacognitively reporting on their correctness when it's difficult versus when it's hard or not? We wanted to investigate time spent on questions, and then we also wanted to maybe try metacognitive training as seen in this study by Jason Carpenter. So yeah, feel free to message me if you have any questions. Here's my email. Happy to talk about it. Thank you.